let's get started. So the first thing I want to do is to talk a little bit about the discussion we had towards the end of the last lecture on the joint sets. It's a really interesting problem. I just made an announcement right before the class. Let me show you that. So, on the joint sets, the problem is this, right? So I have n joints. Okay? And I want to estimate this line. In particular, I want to estimate an upper bound tau such that this is guaranteed to be less equal than tau. A trivial upper bound is this, because you cannot be larger than the size of the cross product. And this, in fact, okay, I have to term this problem a little bit different. Let me convert this to this. Okay, you may wonder what's the difference between this and that. The difference is this is what we call a chain joint. Okay, why is chain joint? Because if you draw it at the graph, like this. That's why it's a chain joint, right? What do I mean by this? This basically means you want to form a joint, multi-table joint. Using natural joint and these relations. For example, this can be this is the joint satisfying this condition, which means you use only natural joint operator and you use only relations from this set. And what is this? If you think about it, this is, in fact, if I just do this, I don't even have to involve R3. And this is what we call a triangle joint. Why? Because if you draw them out, okay, I should add it back. They actually form a triangle. Okay? What's interesting is, the next thing I'm going to say is not obvious, which you have to read this paper called skew strike spike. And they give you this bound called AGM bound. So what is this triangle joint? Essentially, the bound for this is this. N to the power of 3 over 2.
What's that?
The bound of this, the upper bound on the size of this object. Suppose each relation is offset n. But for natural joint, natural chain joint, yes, in the worst case, you get this one. So it depends on the topology of U-join. Topology of U-join. And this part becomes very interesting if you extend it to the context of what we are talking about here, cross-validation. Why? Because suppose this is my join. Okay. You may have a lot of different orders to join them together. One order will be, but at this point, you join with what? And this means the order you perform the join, meaning that you go from here to here, you go from here to here, then you come back and join this with this. R3 and R4 itself, they do not join. But by this time, by the time you finish this thing actually join with R4 because of R2. However, this is impossible. This is impossible. Okay? So the point is there are so many potential orders that you need to consider. For example, you can also do this and then come here. Or you can just do this, come back here, then come here. Or you can even start from here. Who says we must start from here? As you can tell, if you enumerate all the possible join orders, the search space is going to be huge. You follow me? So the left deep tree for the join does help eliminate some of this search space, but it doesn't completely address the problem, because even if you constrain yourself to this left deep tree join topology, you still have many different possible orders to form this tree. Do you follow me? So this is still a very challenging problem, even if you limit yourself to the left deep tree join. Okay. That being said, if you're interested, go read this paper.
What's the triangle join?
Triangle join is this.
Yeah, but why would we join R1 again?
Well, this has, for example, this has a name, join with name, has age, join with age. This has a location, join with location. That's entirely possible, right? I want to find the NBA player has a name with a, NFL player, that share the same name, who happen to have the same age with baseball. What's the name of the baseball league? I don't watch that for years. I forgot you forgot the name. What's the National Baseball League? MLB, or Major League Baseball. Okay, MLB with the same age. Then the player with the same location with the NBA player. So I'm gonna find this loop. The NBA player with the same name with the NFL player who happen to have the same age with a Major League Baseball player, and the Major League Baseball player who happen to live in the same city as that NBA player. That's an interesting question to ask, right? You may wonder why you bother to ask this. I don't know, maybe they all perform really well. They all happen to be MVP, right? There are some correlation I want to test. So that gives you a triangle join. The argument is no matter how you arrange the values of the records in R1, R2, R3, I give you the freedom to generate arbitrary records as you want. Arbitrary values meaning the join attributes. Other values, doesn't really matter. They don't even matter. No matter how you generate values on the join attributes. Okay. Of course, in addition to this, you may have, I don't know, nobody cares. those are irrelevant. But the point is, no matter how you generate the values for A, for B, for C, no matter how you generate those values, you upper bound this for n record for each state. What about general join like this? Or even cycles, right? So I'm going to do this. And this quickly become, as we can tell, it quickly become a very challenging problem. So we're not going to talk about this. We focus on simple chain join, and we focus on left deep trade for for chain join. Not necessarily natural join, but we focus on chain join and left deep trade. You follow me? Even for chain join, keep in mind, you still have many orders to do this. Why? Because the last time we said, I think someone mentioned in last lecture, I think it's actually wrong, which is for a join with k relation, what are the number of possible ordering you have? I think one you said is k factorial, and I confirmed that. Actually, that's not right. Why that's not right? Because you cannot do this order because they do not necessarily join. So what is the right order?
Number of parenthesizations.
The observation is you can start from here. The point is you can start from any of one of this. As soon as you join with a relation, for the existing part, any permutation will be able to join with the remaining ones. For example, my point is, once you have joined this, okay, the next one in order must be one of the two boundary nodes, neighbors from the boundary node. That's the only constraint. And if you follow this constraint, you can easily generate all possible orders. That's the only constraint you need to remember. Take the existing one as a black box. You view this as a black box. That's your existing. So if you want to find the possible order, this actually can be done using a DP formulation again, because a subproblem view as a black box. The next one can attach to the order is gonna be the neighboring node of the two boundary nodes. That's it. You follow me?
So we could never flip the order of any of them?
You can within the black box.
Or anywhere really, like overall we couldn't change the
Well,
order.
I say this is the DP problem because if you view this black box as the number of possible ordering for this many relations that are already in the black box, that's the number. Suppose you know the solution for that. Given that solution you can solve, when you expand the size of this by 1, you can calculate what is the possible number of ordering when you add one more relation, which is the neighboring node to the boundary node.
But you can swap them around if they're joining on the same attribute.
You can, yes, of course.
But in general, you couldn't necessarily.
You could not necessarily, for example, R1 and RK, they're not joining each other. So you cannot join R1 and RK together in the order.
So would it just be then the number of like parenthesizations of the join expression?
No, you mean what's the total possible orders for this?
Well, the total different ways that you could do this.
Totally different way, like I said, is actually not that trivial. I think the only way to solve that is to you do this DP formulation as I said. That will definitely give you the answer. You calculate this and you figure it out.
Because it seems
Actually, you don't have to run the DP because I'm not interested in finding. If your goal is to just calculate the number, this number, this is the recursion expression that you can write it out and calculate it. But if you want to list out all the possible orders, then you have to use that. What I said.
Yeah, it seems like it just boils down to like the number of ways that you can parenthesize the expression.
Well, but with 3 it's tricky, right? Because
can't change the order, but maybe, well, I guess you can change it if you have two, you can swap them.
Okay. Parenthesize the first R1 through K minus 1, then you can put RK on the front.
Yeah, so it's more than.
Well, the point is, if you think about this example, right? Oh, okay, so it's a chain. So for chain, what you're saying is right. For the general topology, that might not be right, because if I have one more here, I can actually jump to this node from any point in this chain, because as soon as I've gone over this node, I can either keep going this way, or from anywhere in this chain, I can come back to here. And any combination of that would work as well. But for chain, then you are kind of limited, because you can only expand to neighboring node.
Well, I guess we could say.
Okay. I think that's, I don't want to spend way too much time on this. And let's come back to this next slide. But my point is, this is actually a very deep topic. Right? If you want to fully understand what's going on, it's a very deep topic. It's not that trivial. So we talk about equivalence. I think we're done with this. We finished the discussion of all this, the size estimation. We explained these formulas. Okay. And now once we know the relational equivalence, that gives us the tool needed to generate equivalent plans. So we basically, the next thing the pre-optimizer will do is to enumerate all possible plans using the relational equivalence we have just established. So I will enumerate all possible plans, and for each plan I will estimate the cost of that plan. And to estimate the cost of a particular plan, we rely on two things. One is size estimation, because you need that in order to derive the size for intermediate joint output, or intermediate selection or projection output. And once you know the size of all your input relations, whether it's a base relation or intermediate results that you have estimated, and you know the algorithm you're going to use for the current operator, you can already estimate the cost of this estimator. Okay, so that's essentially the whole pipeline. How you do this. Okay? For single relation, this actually is kind of trivial. We introduce something called access path. I think we talked about this before, which is access path is one way to physically access this relation, meaning either a heap file scan or index search through a B-tree index or hash, or if it's a sorted file, you can do a binary search. Basically, a physical way to access records in this relation. And any one different way of accessing records in this relation give you one distinct, unique access path. Okay? So, for a single relation, you consider all possible access paths. Why? Because for single relation, you're not going to have too many access paths anyway. So let's just consider all of them, and then you simply choose the one with the least estimated cost. For example, if I do a heap file scan, I know the cost is linear. If I do a B-path tree, I know the cost is log B of roughly n, and where n is number of leaf level pages, and so on and so forth. Of course, you have to take into consideration of the selectivity, because when you say that when you claim the B-path tree range search is log B of n, that's not entirely accurate, because that only gives you the cost of traversing down the tree. It doesn't give you the cost of retrieving the record in the range, which will be, in the worst case, equal to the linear scan. So selectivity plays an important role here in order to get a good estimate on the cost. In the extreme case, if you are selecting everything, then forget about B-path tree. Even if you have one, you should just go with heap file scan. So those are the things you want to take into consideration. Okay. So let's look at some specific example. For example, if you have a B-path tree, how do I estimate the cost? Well, if you are searching on, if you are doing a equality search on the key, here the key is not the search key of the index, but the key of your schema. So either a primary key or candidate key. Then you immediately know that there's gonna be only one matching record. So the cost estimation for this will be the height of index plus 1. If it's a cluster index and you're talking about range search, then what you're doing is the number of pages in the index plus this times selectivity. You may wonder, okay, isn't the case, isn't that this value should be simply the height of index plus number of pages in your file times the selectivity? Do you follow me? I use this as my selectivity. Okay? For range search, you may argue the cost of using p-path index should simply be this: height of the index plus number of pages in your data file times selectivity, because that gives me the number of pages needed to store all the records in the range. But why the slide says is plus okay? What's the difference? Of course, there's a huge difference, right? Because this actually is going to be much bigger than this, right? This essentially, the number of pages in the index, by the way, we derive this, we analyze this, it's going to be linear to essentially the number of pages in the leaf level, essentially. Because the entire size of the index essentially is bounded by the leaf level pages. Why? Because this whole thing add up together is, right? We argue that. So this is a value that between n and the 2n, essentially, the number of pages in the index. Where n is, this n, by the way, n is not this. N is number of leaf level pages. N is number of leaf level pages. Not this, which is going to be much smaller than this value, by the way, which is number of pages in the data file. You follow me? All of you, do you follow me? Questions? So why we do this? Well, the assumption here is that not only you are retrieving the records in the range, you are retrieving the data entries. Suppose you want to ask for both, then you do this. If you only ask for records, then this is your cost. But if you want to retrieve both the data entries from leaf level and records from the data file, this will be the cost. Why? Because this is essentially, like I argued, the size of the index essentially is linear to this. And if you do, if you try to retrieve data entries from the leaf level, how many pages you're going to access? Well, total number of pages times the selectivity, which is essentially this times the selectivity. You follow me?
Why do we want the data entries?
Why do we want the data entries? Well, in query processing, oftentimes, because if you think about this as one operator that may be in a query execution tree, if you want to join, for example, join sailors with reserve and print out the sailor name, in that case, you need both the sailor record to get the name, but maybe you only want to use the entry with the sailor ID to perform the join with the reserve table. You want to do the join with a full record. Give you one example of this. In particular, retrieving this is so cheap because you are already at the leaf level. This, by the way, this is going to be much larger than this. Number of records in the data file is going to be much larger than this. And these are sequential scan anyway. So it's so cheap to retrieve them, so why not we just retrieve them anyhow? That's kind of the argument. And that helps you to do the join in the...
But if you're already pulling out the number, the pages from the actual data file, you can recreate the pages.
You can recreate, yes, you can recreate that on the fly.
Do an IO.
But the overhead of that versus retrieving this, who is winning out, is not clear. So, and it is so cheap to retrieve this anyway, because you are already in that point in your index. You are doing sequential scan anyway, so, okay. But, you can also estimate simply like this. The height of the tray plus number of pages in the data file times the selectivity. That's good enough. For non-cluster index, yeah.
So do you still have to add the height on?
Well, yes, you do, but you know, it's compared to these values. For non-cluster index, this becomes even more clear, I think, given the discussion we have, which is, first of all, you still need to do this part because you need to retrieve those records, which occupy in expectation this many pages. At the same time, you do need, now it's not an option thing, it's not an optional thing anymore. You do have to retrieve all data entries. Because what you do is you do linear scanning in the leaf level, you go up and down to retrieve the record. So you do have to take into consideration of the cost, the I/O cost of retrieving those leaf level pages that contain all the leaf level index and leaf level data entries in the range, which is essentially this value here. The number of pages in the index times this selectivity. Okay? Sequential scan is very simple. There are some examples. I think I'm going to skip this because this is merely application of this, which you can read on your own. I think it's very simple. Now, first on multiple relations. First on multiple relations. This is where that's interesting. That's essentially my opening remarks today. Right? So we consider this, by the way. This is what we call left deep tree join. Let me define. I defined it last lecture, but let me recall the definition once more and make it formal. Right? The argument, the definition is as follows. First of all, it's a tree structure. It must be a tree structure, meaning that there is no cycle. Because once you have a cycle, it turns from a tree to a graph. So it must be a tree, meaning there is no cycle in the topology. And look at every single node in this tree. So in this tree, there are 3 nodes, right? Except the leaf level node. Leaf level node is trivial, we don't consider that. For every single internal node of the tree, you check the internal node of the tree, the right-hand side must be a base relation from U join. The left-hand side can be a base relation or an intermediate join result. And that's how we define a left deep join tree. Okay? So you check, for example, this is the internal node. The right-hand side is a base relation, left-hand side can be a base relation, but in this case it's not, it's an intermediate join result. Why this is not? Because there is an intermediate node whose right-hand side is not a base relation. Same goes here, same argument goes here. Okay? So that's what we call left deep join trees. And then the challenge now, so the only missing puzzle of Q-optimizer, if you follow the discussion along with me to this far, it should be clear to you all that's left to do is to enumerate all possible left deep tree join topologies for a given join. Because once you can enumerate all such plans, given a plan, you simply estimate its cost. Do you follow me? And that completes the Q-optimizer, because you know how to optimize single relation, now you know how to optimize multi-relation. So next we will talk about how exactly we're going to do that. Enumerate left deep tree join plans and estimate the cost of that. Then with that in mind, we're done with Q-optimizer. Okay. So how do we do this? Well, the first thing we do is find what we call first of all, the algorithm proceeds in rounds or in phases or passes, right? So in particular, it goes on for n pass if there are n relations to join. If there are n relations to join, this algorithm will proceed in n rounds. And in pass number 1 or in round number 1, you simply find the best one relation plan for each single relation. So you have n relations. In round 1, you consider them separately, independently from others, and you just look at, okay, this relation, what is the best way to execute my one relation operation on this table? By one relation operation, I mean selection projection, pretty much selection and projection, okay? And where those selection projection comes from Well, those selection projections come from U-join. So U-join, keep in mind, is not necessarily a natural join. They may be it could be a natural join over relations augmented with additional selection and projection conditions. And we use relational equivalence to push down those selection projections into the respective relations to form these one relation operations that we consider here. Is that clear? Give you example. If I do okay, that's a join and selection. What is my one relation plan that I consider in part one? Well, you use relational equivalence to push this inside, and in one relation plan you consider in part one is what? And reserve there's nothing going on, so you simply just do that. However, a sophisticated product manager might argue my one relation plan should be this. You follow me? You may argue what is really the difference. In order to do this, don't you have to do a linear scan of the relation anyway? Well, that depends, right? If you have an index on reserve that happens to be an index, the search key of the index happens to be SID, you still need to do the linear scan, but you can do the linear scan using the index, using the data entry in the index, rather than linear scan the records. So there's still a subtle difference. Why? Because the size of the leaf level pages is much less than the size of this. So scanning leaf level pages is going to be much more efficient than scanning this. So it still makes sense for you to push this down, to do relational equivalence to project this down. But that said, my one relation is this. And it's simply linear to the number of relations involving a join. So you have n relation join, you have one relation plan that you need to consider. And for each one relation plan, you find the best way to execute that. That's in part one, that's trivial. Okay, so you use relational equivalence, and the way we just talked about how to evaluate one relation plan to carry out pass number one, to carry out round number one. Any question on round number one? Okay, so the base case should be pretty clear to you, right? Pass one is clear. But at the end of this one, so that's my pass one. What do you get? You get the best way to execute this and the best way to execute this. Right? Given the cost estimation and all that stuff we talked about so far, right? You use all this information, you know how to execute this, you know how to execute this in the most efficient manner, given your database setup. What's interesting is what happened to pass 2 and pass 3 and pass 4, the following rounds. Those are interesting, right? So let's look at pass 2. I think once you understand pass 2, pass 3, 4 until pass n is simply a recursive application of what you do in pass 2. So all you need to do is to understand pass 2, then you're done. Then we're done with this algorithm. Okay? So what do you do in pass 2? The pass 2 says you find the best way to join results of each one relation plan as order to another relation. Okay, using this example, what does this sentence mean? What this sentence means is you do a round robin iteration over all these one relation plans. Okay? So and you use this as order to relation. And you consider joining this with another one relation plan. Joining with another one relation plan. Meaning this is the order joined with this. If you do have a third relation, that's for the argument's sake. Let me just make it clear. Let me add. How about we add both and I have another selection called color equals red. So in my pass 1, I have to alter my one relation plan that I consider, which will become potentially with this. Okay, and in fact, if I do projection, then I should project out what? Suppose your final goal is to project out the Saturn A. Okay. Then what I project out here is, and once I done the selection, I no longer need the rating value in the projection. Yes or no? Of course, this becomes, there's a subtle issue here. That's what you want. The best one relation plan, in the process of evaluating which is the best one relation plan, you will consider doing this first, then this, or doing this projection, in that case, with the rating value, and then do the selection. But at the end of the day, those details are abstracted away from the, from the view of pass 2. I don't care how, you just tell me how to do this. You follow me? Okay. Now in pass 2, what I do? In pass 2, I consider all the possible ways to join this, to join every two of them. That's the way you view this. You consider all the possible ways to join every two relations. To join every two relations. You take this, and you join with this. And you take this. Do you consider join with this? Yes, you do, because when I do this, when the arrow goes this way, this means this is the order. So when I draw an arrow like that, that means so you also do consider this and this. And finally, what do? You consider this and this. Yes? And immediately you say this is a quadratic, right? This is a quadratic cost. Isn't that prohibitive for the cross method to do this? Well, the observation is when you rarely see join over like 8, 9 tables. Typical value of n is like 5 or 6, and n squared was 36. And with today's i7 processor, 36 is like, come on, if you tell him to do 36 plans to estimate the cost, I may have 16 cores, 32 cores, and each core just do 1. Because at this point there's no I/O involved, so multi-threading really helps. You can execute, you can evaluate each plan, the cost of each plan in parallel. All this can be done in parallel, right? Think about it in multi-core architecture. Okay, and that's pretty much you pass 2. Of course, I haven't finished pass 2 yet, but that's a major step in pass 2. Now, you find the best way to join results of each one relation plan to another relation. What that means is, now let me erase all these other errors. Clear. Okay. So 1, 2, 3. What do I mean by this? Well, this only tells you the order, which is this is the outer, this is the inner. But it doesn't tell you what is the algorithm for doing this line, for doing this join, right? I could do a page-oriented nested loop join. I could do okay, think about flying from Utah, Salt Lake to New York. This only tells you are flying from Salt Lake to New York. You are not flying from New York to Salt Lake. But you can fly United, you can fly American, by the way, you should try to avoid American if possible. And you can fly with Delta. Right? So those Delta, American, United, those are your joint algorithms. And you haven't made a decision on that yet. The point is, this is where this becomes a heuristic algorithm rather than an exact accurate algorithm. Because if you want to find the exact optimal algorithm, even with regard, by the way, we already cannot find exact algorithm because we only consider left deep join trace. That already get rid of a lot of search space. Maybe the optimal plan is in one of those places. But even if we consider just left deep join trace, we are not able to find even the exact optimal for this. The reason is, in order to find that, you need to keep track of not only all these possible orders, but for each ordering, different ways of flying that path. And that combination quickly becomes out of control. Even for a small value n, that combination is simply too expensive to keep track of. Because you have so many different ways to do this. Like even from pass 1 to pass 2, you already lose information. Because maybe, okay, doing this using a B path tree is faster. But once you consider this, maybe you should not do a B path tree, you should simply sort this. Because that gives you doing the sort merge much faster in second round. But we already make a local decision. The point is, you are making local decision at each pass. And that's a compromisation you have to do because the global optimization is simply too, even for small value n, it's just too expensive. Okay, that said, once you consider this order, you can view this pretty much like the problem you have considered in part 1, which is this is the unit, order is fixed. Just tell me what's the best way to execute this unit. You view this as a black box. Whether this unit has 1 relation or 2 relation or 3 relation, you don't care. For each such unit, you remember only the best way to do that unit. You follow me? And this pretty much boils down to the same thing as what you have done in part 1, except that in part 1, each unit has only what? 1 relation. But now each unit has what? 2 relations.
So it's almost like we're building the trees like bottom
Yeah,
up.
bottom up, yes. Building a tree bottom up. So in part 2, how many such units you have? I just argued, right? For 3 relations, you have 9 such units. And for each such unit, what do? You remember the best way to execute that unit. You view this as a black box. And then you are done with part 2. And what do you do in part 3? Well, here comes the tricky part. You do not join one unit with another unit as what you have done in part 2. In part 2, if you think about it, it looks like if you use this unit view, you are joining one unit with all possible units, all other possible units. In part 3, you should not do that because once you do that, you do not get a left deep tree join. Right? Because each of this unit is what, by the way? Each of this unit is, if you look at that, is something like this. Or maybe each of unit looks like this. If you join these two, for example, you no longer get a left deep tree join. You get something like that, right? If you try to join these units together, right? So you should not do that because that's not something we ought to consider. We said we eliminate all of these guys. So what do you do in part 3? The reason we do not do this, by the way, is subtle, but you can tell that if you try to do that, then the growth of this become exponential. Why? Because you start with n, you get n squared. If you try to join the units, you get what? Next round you get n to the power 4. And that becomes exponential growth. You cannot afford to do that. So what do? Well, you grow this by another n. How can that be possible? You simply join the unit with just the base relation again, which you only have n of them. Okay? And that form yet another new unit. And the size of the unit grows by 1. And each unit, by now you should realize that each unit is nothing else but a subtree in this left deep tree joint graph. And what do? You keep, again, the best way to execute that 1 unit. By now, I think you should understand this diagram, right? Just proceed. You're done. Do you follow me? That's the entire algorithm. We're done. That's the entire algorithm. We're done. Okay? So for each subset of relation, that's essentially for each unit, such unit I talked about, which is the subtree from this left deep tree joint. You keep the best plan overall, and use that in next pass. You use that in next pass. Of course, by doing that, you are losing potential optimization opportunities, as I argued, right? For example, in pass 1, you use B pass tree because you did a local decision, but then you realize to join with another relation, the only join I can do is sort merge join. Maybe I should go back and do a sort merge, do a merge sort on my relation in pass 1, so that I can do the join in second pass almost like for free. But you don't do that. The point is you don't backtrack. In this algorithm, you do not backtrack. You make a decision, never look back, move forward.
Is this the way it's done in real life, or is this kind of a simple?
In real, pretty much actually, because if you try to consider that unit join with unit, then you get this growth. This versus look at the speed of the growth. Furthermore, even if you do this, by the way, even if you do this, is that going to give you the exact solution? Hell no, because from here to here, you already lose the chance of finding that solution, because the combination is not only n to the n to the power 4, but for this only tells you the order. That's the key observation. It doesn't tell you. It only tells you fly from Boston to New York to Atlanta. It doesn't tell you whether I should fly Delta on the first leg, United on the second leg, or any combination of all. It's become creative if you think about it, right? So this only tells you the different way of arranging, like flying n cities, how do you fly between them. But it doesn't really tell you what airline you use for each segment. So even if you do this, you don't get the exact optimal solution. And let alone this itself is impossible to do. So you go with this. And you go with this, and you make local decisions. Like I only consider which airline I should fly from Salt Lake to New York. And once I make that decision, I never come back and revise that.
Seems like this would be a good candidate for dynamic programming, but I guess, I mean, if that were the case, then somebody would have done it. If there was any kind of overlap.
So one way to think about that is you try to formally go through the process, analyze what is the cost of dynamic programming, blah blah blah. On the other hand, you can prove this, from this counter argument, which is to consider all possible sequences, different ways of possibly doing this. No matter whether you use DP or any other algorithm, if your goal is to find the exact solution, you have to look at all possible combinations, and that itself, you cost. Okay.
Well, not necessarily if the solution is based on the solution of the subproblems and somehow and see.
I see what you're saying. But yes, totally. But unfortunately, that does not apply here. The point is, the optimal solution for the sub problem is not going to give you the optimal solution for the global solution. That's the key constraint for you in order to apply DP to cut out the search space. But it doesn't happen.
Why do we start from the bottom instead of from the top? I mean, my thinking on this is, if we start at the top and make recursive calls down, then at some point, on some of the recursive calls, we might be able to feed in information that says, oh, it might be useful to have, the whole relation sorted on this output. Does that make sense?
Yeah, it makes sense. But my argument is, if you think about it, that top you talk about, suppose you are referring to the top of the final output. You know this is my output, and there's a top, because otherwise top is not well defined. This relation, topology-wise top is defined, but who is at top is not well defined until you see the output. My point is this argument, once you give me the output, my argument is that output at the top, the relation at top, was considered at the bottom to begin with. It just doesn't win out in this competition as a bottom relation. We did consider that.
Yeah.
Make sense? So topology-wise is well defined. That's the node at top. But the content of the top is not defined until you see the output. And my argument is, once you give me the output, my argument is that relation at the top was already considered as the bottom relation. The way we do it. Any?
Well, going on with that, I mean, couldn't you say,
Yeah.
like, going from the top, you have two branches, and then on the right branch, you're going to have a base relation. So couldn't you say, I'm going to choose an arbitrary base relation, and then recurse on the rest and get an optimal?
I think you can, but my feeling is that will basically give you the same thing. I will basically give you the same thing. If in each level you consider, for example, you pass one become every single relation is you keep the best one possible path for each relation to be the top, and so on. So I think this will give you essentially the same thing.
But then, like Monty said, like you could say, like suppose you know the relation you choose is like really small, so you could say, oh, I can do like hash join, and then I pass down that information, so you recur on the left branch.
My argument is going down top or going down bottom. If you enumerate all best possible local plan, like what we did here, I think these two arguments are essentially the same. That's one thing we haven't considered is the selectivity of intermediate results, right? So, for example, if you know one relation among this batch, one relation plans, that one of them has the smallest size after doing the selection, whatever, right? In the extreme case, it becomes only one tuple. Then an obvious optimization is you should simply keep that as you base for growing this left deep trade off. Does it make sense to you? Rather than thinking about all these possible two-way, that's a global optimization you can do. So those additional optimizations I didn't discuss here, and that's where the difference is between this and those optimizers used in Oracle. And those are typically called rule-based optimization. Why is rule-based? Because based on your experience of running your database server for so many years, you realize when the relation is this small, just do this, forget about this. So it's a simple rule-based check. And what I know is in Oracle DB, they have about 400 some rules for rule-based optimization. And if you remove those rule-based optimization that Oracle has done, their optimizer is not much different from this. But those rules, you can call them rules, but the real name is those tricks or hacks. You can only learn that by being Oracle. Seriously. Can Microsoft do this? Can Google do this? Hell no, because you do not have enough data or use case for you to derive these rules in the first place. You see what I'm saying? You only get these really nice rules after you have so many customers, you have so many installation of your database instance, and you learn your lessons over the years from customer feedback. And that's why, and the same thing actually extends to the computation in search engines. What is the difference between Bing and Google? Well, the base algorithm is the same, kind of like this. You grow, of course, they don't do growth, they use PageRank. By the way, they call this $1 million PCA. Yeah, I think I mentioned this. Maybe I didn't. Why $1 million PCA? What is PCA, by the way? Principal Component Analysis, which is to find the most dominant size K subspace to preserve the variance of your original matrix in a really high dimension. You want to do dimensionality reduction. And why this is related to Google? Because Google essentially models the web as a matrix. Who links to who? And that, if you model the web as a matrix, of course, that's a huge matrix. Who links to who? That's like n website is n square, and n is, I don't know, billions of pages, whatever. So you talk about billions square, that's your matrix. And why PCA matters? Because what Google does is to compute the PCA of that matrix, and then project those pages onto the subspace, and you rank based on that. And this is called PageRank. And there's no secret. So Bing does the same, and everybody does the same. Everybody in the search engine business does the same. But why you see such a huge difference in the search result to this date? Google still is way much better than Bing, right? The reason is, again, rule-based. Because rule-based has no rationale. There's really no reasoning going on. It's really based on human observation over enough data. Enough collection of data, and this become kind of like, this is a closed loop, because if your search engine quality is not good enough, you're not going to attract enough user to use it. If you don't have enough user to use it, you do not have enough user data to make good rules to optimize. And if you don't have good rules to optimize, your quality start to be worse, becoming worse than the other one. So more users will use that, and you start getting less data. And it's less likely for you to get optimized rule, and then you lose out. Initially, the gap is maybe just a little bit, but as you can tell, it's become like this. And there's not much way to fix this unless you suddenly find a new, fundamentally different way of doing this thing. Then you can beat Google. But for now, people haven't found that yet. I would use PageRank. If you use the same algorithm to begin with, I don't think there's a way for Microsoft to beat Google because of this. Unless Microsoft, some genius guy in Microsoft say, oh, forget about matrix. We don't do matrix. We do, I don't know, use this as whatever. I don't know. And then you find a fundamentally new algorithm. Then you can beat back. You can beat Google. Same thing here. Oh, and that's why it's called $1 million PCA, right? Because Google's PCA was like a 40 years old concept, and this founders of Google they applied it for search engines, and they made $1 million off it. And this is the one of Professor made this comment in early 2000. I think he or she seriously underestimated the value of this PCA. It's not $1 million PCA; it's $1 billion PCA. So it's wrong. It's $1 billion PCA. And this, so same thing goes here. If you run, we tested a lot of benchmark in our research group. Our experience is that Oracle is always typically the best, followed by SQL Server, followed by MySQL, followed by PostgreSQL. For the same query, for the same setup, you build the same index, you make sure you have the same physical access path on all tables from all database servers. Same data, same disk layout, same buffer. Oracle always going to be the best because I think essentially the rule-based optimization. And speaking of that, there's an interesting thing called there's a thing called Dewey clause. Read this. So what Dewey clause says is, if you try to write a research paper, or even if you try to post numbers on your website, performance number on your website, you cannot say Oracle, bar 1 Oracle, bar 2 Microsoft SQL Server, bar 3. Open source is fine, like MySQL, PJ, that's okay. You have to call Oracle DBX, You have to call Microsoft DBY. Why? Because back in 80s or 90s, this guy, David DeWitt, he was a professor at Wisconsin. He published a paper, and he said, okay, I did this experiment, Oracle is this bar, this database is this bar, and my database is this bar. And Oracle looks obviously bad, of course, on that result. So Oracle, the CEO, what's the Oracle CEO name? Eric something, right? He called the Department of Wisconsin, and then later called the University of Wisconsin, the president of Provost's office, and asked them to lay off this guy, to fire David DeWitt. Like, they went that far because the number looks bad for them. Okay. And then the university obviously refused to do that. And David DeWitt, I believe at the time, was only an assistant professor without tenure. So the university can easily fire him, right? Because you don't have tenure yet. But they didn't do that. So Oracle spent, like, I don't know, a huge amount of dollars to start a legal case against University of Wisconsin and David DeWitt. Then the final outcome of that, they settle it, is that no research paper or online performance benchmark can mention the database name you use. And it goes this far, like in today, if you write a paper, you cannot even call this as database O, because that's obviously what you mean, right? You cannot even call it O. And so that's essentially what happens. So it's interesting. Larry Anderson, not Larry Anderson. And this is called the DeWitt clause. Imagine, to appreciate this, it's kind of like tell the car dealers, okay, the commercials, you cannot show Toyota versus Ford. You have to call car T versus car F. You know what I'm saying? In order to compare two cars, you cannot do that. Essentially, that's what this clause means. If you think about it, it's kind of ridiculous, but that's what it is. It's a crazy place. Right? So it's kind of like we try to negotiate something, try to decide which product to buy, but we have to talk secretly without revealing the product name I'm talking about. I said, oh, this X is better than Y. And you say Y is better than X. And we cannot tell each other what is X, what is Y. Somehow secretly we have to exchange that information. So, okay. So, and one last thing on this algorithm is, in addition to the best plan in each level, right, for that unit. In addition to that, we also consider something else called interesting order. What is an interesting order? The interesting order means the following. It is not the best way to join this relation inside this unit. This unit could be a 3 relation left if pre-join or 4 relation left if pre-join. That's what this unit is. In the current algorithm, we simply keep the best way to join this using this local greedy algorithm, right? The best way to do 1, best way to join this 1 with another, then the best way to do this 2, the best way to do this 2 with another, the best way to do this 3, that becomes the best way to do this 3. Quote unquote best, because it's not going to be the best overall. It's the best local decision you have made. In addition to that, what do we keep? We keep what we call interesting orders. Interesting order here, the order doesn't mean the order to join these relations, but interesting order as in terms of the final output. For example, maybe my best way to join these 2 units with another base relation is to do hash join. So A join B, I already know what's the best plan to do A join B. That's determined from the previous path, from path 2. So in path 3, I try to find the best plan to join A, B, then join C, right? You follow me? Currently, the algorithm says I try all possible ways to join A, B, then C. I keep the best. Let's say the best is hash join. In addition to that, what do you keep? Let's say later on, in the output, there is an order by A dot name. Order by A dot name. or ordered by B.name, or ordered by C.name. Let's say ordered by C.name. That's the easiest to understand. So there's the order by clause in your query, which is to order the entire join by an attribute from relation C. And that attribute happens to be your join attribute between C and AB as well. Now, what is the interesting order? An interesting order is to join AB with C using sort merge join. That's what we mean by interesting order. It's like I said, its efficiency is not as good as joining A, B, and C with hash join, but because you have an order by C.name, and name is your join attribute between C and AB, doing this sort merge join between A, B, and C make both A, B, and C sorted. Even though the cost is higher than doing a hash join, but down the road, you can do this order by for free. So you're killing two birds with one stone, even though this stone has this step has a little bit higher cost than doing hash join, but you're saving cost down the road. And this is what we mean by interesting orders. Okay, so that said, in each of this step, when you do the unit join with another one, you keep two things. One is the best plan to do that, and the best plan to do an interesting order. That best plan to do the interesting order, the cost, the best case you can hope for is that happens to be your best plan overall. Then fine, you just do that. But most likely it's not going to be the same. Then you keep both of them, so that down the road you can evaluate again which one is better. And you may argue, isn't that going to introduce a lot of overhead, meaning that for every such consideration, meaning join a unit with another base relation, do I have to keep two plans now instead of one? Well, chances are, in most cases, you only need to keep the best plan, because the interesting order doesn't happen that often. What are some examples of interesting order? Which is explained in the next slide. Group order by and group by, that's easy, right? Order by, why order by is interesting? Because that means maybe doing a sort merge join is interesting, even though it might be more costly than another local join algorithm. And what about group by? Well, group by means maybe you should consider using either hash or sort merge join, even if they're more expensive than block nested join, because that gives you the opportunity to do group by much more efficiently down the road. If you see in your query block, you're going to have a group by in the end, and this makes sense to do. And that's the additional interesting order you should keep. By the way, this is the in addition to the best plan you keep, meaning that you never throw away the best local plan and keep the interesting order. It's that you keep that, and in addition to that, you keep interesting order. And the last one is not so obvious, actually. Order by group by, that's obvious, right? The last one says the join attributes of yet to be planned joins. What does it mean? Well, I'll give you a simple example. Let's say A join B and then C. And the join between A and B is unnamed, and so happens that the join between B and C is also named. Okay? But your local plan tells you A join B, the best plan is hash join. Not a hash, let's say next loop join. It's better than, it happens to be better than both hash join and the sort merge join. However, there are no group by order by involved, by the way, in this case. However, because the fact that you are joining name with C, and you happen to know C is already sorted by name, then what is the interesting order? Well, interesting order is join A and B with sort merge join, even though it's maybe more costly. Why? Because once you finish that, you can join A, B, and C almost for free, because C is already sorted by name. That's an example of this join attributes of yet to be planned joins. Okay? Well, the other thing, the last thing I want to argue is, and then I will go example with you. I think then I will call it a day because I don't want to start the discussion on transaction because that's another big monster topic. And co-optimizer is this. The thing we talk about today is really one of the most challenging parts to understand in the course, right? But I hope by the discussion today we have a really good understanding of what's going on. Once you understand the principle of what you're doing, essentially to summarize the principle, which is you do local greedy optimization, this whole thing becomes clear. And constraint on, of course, you do local greedy optimization and constraint on left deep tree joint graphs. That's pretty much what you're doing. Once you understand that, you should be able to understand this. But in the past, of my experience, a lot of students, they cannot, first of all, they cannot fully understand this left deep tree joint thing. They understand this graph, but they don't know how to enumerate all the possible left deep tree joint graph. And that's why they cannot really appreciate, oh, you are really keeping the best local plan, joining one sub tree from this left deep tree joint with another base relation. Sometimes they think, oh, I'm joining. I find all two relation join, then I find the best way to join them. That's not right, because once you do that, you get that growth rate instead of that. So those are little things that you need to pay attention to. One last thing is, when I have a growth rate of this actually is the worst case growth rate. Why? Because a lot of them, they do not join actually. For the argument I give you, right? I mean, these guys do not even join with this. So this growth rate is the worst case growth rate. Because you do not actually consider, you do consider every unit join with another relation, but you only actually consider it if there is a joint condition between them. If there is no joint condition, you check this, you ignore. In other words, you do not consider cross product in the process of doing this. If you consider cross product, yes, the growth rate is precisely this, but if you throw away the cross product, your growth rate is going to be much, much less than this. Do you follow me? Yes or no? Think about this. These two, you do not jump with this. Do not jump with this. But maybe your original joint condition is like that. Then yes, you have to consider this joint with this joint with this. But if you joint order is, you joint topology graph is like this, then you only consider this joint with this. Yeah? So that's the final note we have, and then there's some other stuff. So basically the stuff on slide is what I talked about already. Okay, now let's consider an example. We're not. Okay? So what's this example? I have both reserve setter. So it's a three table joint. Okay? Three table joint. And my database catalog returns those information to me. The catalog tells me that I have a hash on B plus 3 on SID, class B plus on BID, B plus 3 on CID, B plus 3 hash on color. Okay, that's my catalog. And this is my query, right? But like one of the query you have written in your midterm test. Okay, now you see how far we have gone, right? From writing SQL to relational algebra to understand how this is translated to relational algebra, not all the way to understand, oh, I actually can massage this in different ways and to evaluate the cost. So I convert this to, next time, whenever I type SQL, I do not think about SQL, I actually think about this when I type SQL. And in the future, if you become a database administrator for some company, that's what you should be doing as well. When you type SQL, when you arrange your tables, think about this rather than this. Because this actually is simple now, right? To think about it. To write what you want is simple. To understand how to do it is the database, how database does it is not simple. So that's my translation. That's just a direct translation of this. I have a selection on color, join with reserve, join with setter. Okay, and I have Kuba and projection. Okay. Pass one. What is my pass one? Pass one is both reserve, setter, each in their own, and carry out the one relation plan. Find out the best one relation plan for each single relation, independently from the other relations. So for reserve and setter, no selection condition, What do I do? Key false scan. Nothing, no other choice, right? There is no selection, but nothing. Suppose we do not consider, by the way, suppose we do not consider this projection I talked about. In this case, I consider pushing down the projection. In this here, we do not consider that. If we do not have that, the best one relation plan for reserve and sealers are trivial, key false scan. What about boats? Boats, we have to look at the catalog. We have B-part tree and hash on color. Wonderful. That's actually my search condition. I can use that. Which one is more efficient? Well, for that, you need to look at the selectivity, first of all. Why selectivity matters, by the way, in this case? Well, if your selectivity is very high, by the way, selectivity high means you are selecting very few records. Then using hash index is a good idea. If your selectivity is low, B+3 is a better idea. Why? Because hash index not necessarily sorts their data entries or the records. You may have millions of red color boats that scatter around in this one big bucket. You still need to do linear scan of that bucket in order to find all of them. That could be very expensive. But if I have a cluster B+3, this is fairly efficient. So that's another tricky thing. It doesn't mean automatically you quality search hash is always going to be better. It depends on your selectivity. Depends on your selectivity. Yes or no? So that's why at the end of my pass one, let's say I keep both B+3 and hash. Let's say I cannot make a decision which is the best. I keep both of them, or you simply choose one of them randomly. You follow me? So that's my output. Pass one. Pass two. You see how this goes, right? Do I need to explain this? That's pretty much right? Each one relation and order joined with another. Consider all possible combinations. Take a minute to look at this. That's essentially what you do. Yeah? Okay? And then for each pair of relations, you keep the best plan. For each unit, you keep the best plan to do that. That's precisely what we said just now, right? For every pair, you keep the best plan. And path 3, for each of the plans returned from path 2, treat it as order. By the way, at this point, the unit from path 2 must be the order because you are considering left deep tree joins. And the right hand side is your base relation. So whatever from the preceding path must be the order. They cannot be the inner because once you do the inner, it's no longer a left deep tree join. Now it becomes a right deep tree join. Nothing wrong with it, but we have to be consistent because left deep tree join and right deep tree join and left deep tree join are symmetric essentially. But to be just consistent, we only consider left deep tree join. You consider those plans from path 2 as order and add, this is important, add only base relation to the right hand side, not those other plans from path 2 as inner. Only the base relation as inner, not those other plans from path 2 as inner, because if you do that, you get this. And furthermore, when you take those plans from path 2 and join with the base relation, only consider the one that you actually join. Do not consider a cross plan. For example, you have a both hash and color with reserve, which is inner, which is soft merge join, which is hash color with reserve, which is this one, right? This one. You take that and you inner join with B tree. With B tree on CIE over sealers. That's you. And then finally you add the cost of doing goodbye and the aggregate. And then among the remaining plans, you look at which one is the cheapest. Then you return that to the executor. Next, the query, I mentioned this, we just optimize this block by block independently. With that, I think I'm done with query optimizer. On Tuesday, we start this new journey on transaction. Okay? All right.